Hi everyone, I'm Torben, a PhD student at the CCIMI, and I will talk about particle filters in high dimensions. My idea is to give you a quick introduction on what particle filters are, because I assume that everyone in the room here knows what particle filters are. I'll have one very technical slide, so yeah, those who don't like that one, just ignore it. And then I have some nice pictures in there to light up the room a little bit. Talk about particle filtering first. So we have the following setup. We have some unknown quantity x that we want to infer, and this quantity changes over time by some function f, and there is also some noise involved, and we can't measure this x directly, but we have some kind of observation operator, which is that we have observations y that are somehow connected to the x. That might be that we have a function which we can evaluate pointwise. It might be just a very noisy measurement. And we are interested in finding the filtering distributions. That is, we want to know what is the probability for certain x's given the data until a certain time t. And particle filtering achieves this using a particle approximation to this filtering distribution. Some applications are climate modeling, where we have lots of data that come in over years, but the data comes in quite slowly, so like a few data points every day. So therefore we have a lot of time to calculate models. We might be interested in ocean flows, or we might be interested in the location of some airplane that is flying around, where we have data coming in very fast, but not too much, usually like a three-dimensional coordinate or something. And we are interested in making these particle filters be applicable in high-dimensional settings where data comes in quite quickly, so where one doesn't have much time to compute stuff. How does this particle filtering work? So I have a cloud of particles, which is a sample from the prior, and I take this cloud and pass it on through this dynamics f that I know to get some locations. Now I get a measurement, and I want to compare these points that I have to this measurement. So this is the observation that I have, and the idea in this very simple model is that the closer my points are to this observation, the more likely they are. So therefore I give them weights, so the points nearby get higher weights, and the points that are far away get lower weights, so that I end up with this weighted ensemble now. And I can repeat this step, so now I take this weighted ensemble, again pass it on in time, get the next prediction, and then I can update that again using the likelihood. In high-dimensional settings, however, this doesn't work as well, and the following happens. I do a single step, and I have one particle that has all the weights, and all the other particles are basically not important anymore. So ideally we want something like this. We want uniform weights that are very well approximating this filtering distribution. And now here's the technical slide that is coming up. We're trying to use transport maps to achieve this. So a transport map, the way we want to use it is that we have a sample from a prior, and then the transport map of this sample is a sample from the posterior. So a sample from the filtering distribution. One approach of doing this is one that Heng came up with. It's one takes this following PDE here, defines some measures between the prior and the posterior by kind of gradually introducing the likelihood. And if one has this flow f, which is quite complicated to calculate, then the final location of a particle under this flow f gives us a sample of the posterior. That works, but it comes with some disadvantages, and that is where our future research comes in. We try to come up with methods that are fast and more accurate. So this approach by Heng, for instance, is very accurate when one finds when one can compute this flow f very accurately. There are other approaches. So one is the ensemble-Kalman filter, where one takes a very, very crude approximation, which is very crude but very fast. So we kind of try to find a trade-off of these two approaches. If you want to know what this nice picture here is, meet me at my poster afterwards. Otherwise, thanks for your attention.